All right, ladies and gentlemen, good morning to you guys. I hope you guys are doing well. Give me a like if you can hear me. You know, on my end it says you can. All right, thank you guys so much. Let's see in the browser here if we can beat the calculus class at 39.2. Excuse me. All right, ladies and gentlemen, you have an upload speed of 39.3. That is better than the calculus class at 39.2. So set YouTube to 1080p, maximize your experience. And we are over here working with our exponential functions, ladies and gentlemen. And here you go, exponential functions. This is the work we were doing. And there it is. So just want to remind people today, office hours I have to cut short today because there's a meeting I have to get to. So I'll be leaving my office hours early today. The meeting's around 12:15, so I'll be leaving around 12:10 my office hours, or maybe a little bit earlier. So ladies and gentlemen, that's kind of what's going on. But notice this worksheet. This is what we were working on, and this is a part of the course. Now I'm going to introduce to you guys something extremely important and a very important idea. And here's the concept that we were seeing here, that as we moved to have our interest compounded, hold on for a few seconds. Okay, I apologize. I am back. What we were seeing on the last time we were together, whatever that was, as we increased our monthly payments or annual payments, we were getting more and more money. Remember, we're compounding our interest. And I want us to focus on this n value. This is what I mean. This n value, ladies and gentlemen, as we simply looked at different compounding. N was 1, 2, 4, and 12. So we compounded our interest, ladies and gentlemen, the last time we were together. We compounded our interest more often, more frequent in a year. And so if I said to you, what if we, compounded our interest maybe not every month, but what about daily? 365 payments in a year. That would be pretty good. And then if you said, well, we can do better than that. If it's every hour, it's 24 hours. So this would be hourly. 24 hours are in a day. How about every minute? 24 times 6. This is how we compound our interest. If we compound our interest, how about every second? 60 times 60 here. That's another way to compound our interest. So if we compound our interest this way, more frequent, we should see, ladies and gentlemen, a lot more lush in terms of our money. Remember, this was N is 4. This was N is 12 here. This is what we were quarterly, monthly. Look at the money. It's getting more and more. So if I were to increase this N value, not every second, maybe every nanosecond, more and more payments in a year, we're going to have more money. So this is the idea. What I'm going to say is we're going to let N get arbitrarily large. This is getting arbitrarily large, ladies and gentlemen. This is the idea that N is going to infinity.
To infinity and beyond.
Okay, meaning the number of interest payments you get per year gets arbitrarily large.
To infinity and beyond.
So it's not daily. It's not hourly. It's not every minute. It's not every second. It's actually continuously. And that's the whole idea. To get paid interest continuously, let the number of interest payments given to you in a year go to
to infinity and beyond.
To get arbitrarily large. And that's where this is at. And gets to infinity here. So here's the thing about it. Okay, this is what we call continuous interest. So in order to do that, though, what I'm going to say now is this. I'm going to let N be this ratio. Or let X be. I apologize. We're going to let X be the ratio now. I'm going to have to get some information out for you guys. Okay, I think X is going to be N over R. Yeah, this ratio. I'm going to introduce a new variable. I'm going to substitute this X. So X is going to be N over R now. And what that means then, if I cross multiply, to have N, X being N over R. Is you end up with this reciprocal 1 over X is R over N. So I'm going to do a special substitution here that we're going to use here to talk about how to see things go to infinity there, the number of payments, or to get paid our interest continuously. Not every second, not every, minute, not every microsecond, nanosecond, whatever, continuously. Now, what that means here is the amount we have is A naught 1 plus, this becomes 1 over X. Now, this also means if I solve for N, if X is N over R, this means N is X times R. So this portion here is 1 over X, and this portion here is XR. So we get XR and T now. So that my amount here, A naught, is 1 plus 1 over X. The properties of exponents, remember what you can do, right? If you have X raised to the RT, that's simply XRT. So I'm using some algebra here with this substitution. And what I want to remind people here to do is I want you to focus on this portion right in here. So now we want to focus on this. And I want to draw an ellipse here because I'm partial to ellipses. So I'm going to say here, focus on this mechanism, this X value. Okay, so remember what is X anyway, right? We got this N. X is N over R. Which also means, this N is equal to x times r. R is the interest rate, so r is constant. So what happens is, as we say, as n gets bigger and bigger, like we were describing n here, daily, 365, hourly, 365 times 24, minute, 365 times 24 times 60, these big numbers. Every second, 364 times 24 times 60 times 60. N is getting big.
To infinity and beyond.
And that means x is getting big as well.
To infinity and beyond.
So what we want to find out is what happens to this portion, our focus. What happens to this 1 plus 1 over x, really to the x power as x gets big.
To infinity and beyond.
So what I'll do now for us is I'm going to go into Microsoft Excel for us. I'm going to do something very interesting, right? Let me go to Microsoft Excel. Where are we at? Here we go. So you guys can see, we're going to look at that mechanism now. X 1 plus 1 over x raised to the x power. All right. And we're going to watch this as x gets big now. Okay, so I'm going to start with x is 1. And then 10. I'm going to do powers of 10. 100. Remember, x is getting big.
To infinity and beyond.
1,000. Isn't x getting bigger? 10,000. 100,000. X is getting bigger, ladies and gentlemen. So I got 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros. Okay. So x is getting big. I want to see what does 1 plus 1 over x to the x power become? Because I'm focusing on that mechanism. Because n is getting big, so is x. All right, here we go. 1 plus 1 divided by that number, that cell. Raise that to that cell power. And that's 2. So when x is 1, the mechanism is 1 plus 1 over x is actually 2. Let's see what happens when x is 10. The number's 2.593 and so on. X is getting bigger because n is getting bigger. X is getting bigger. So here's what I want you guys to notice. What happens as x gets big? What you should see is something interesting. I don't remember how many zeros were here. This was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't know. Was that the same? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so as x gets big, let's not do the last one. Let's just keep it as we see here. I want people to notice what's happening here. What do you guys see right in here? This is my point to you. As x is getting big, ladies and gentlemen, what happens to the mechanism? Does anybody see what's happening to the mechanism there? What number? You're supposed to see a pattern here. That's the idea. There's a pattern here. Okay, what happens with the pattern? Do you guys see it? Here's what I'm saying. If I go back to the iPad, this number is starting to repeat as x gets big. That's 718282053. This pattern is repeating over and over and over again. Right in there. at the very end there. And this is what you guys start to see is that number is what I'm referring to here. Now, this number is very special. It's so special that it even has a name, and it has a letter. We represent this with the letter E, ladies and gentlemen. This is called the exponential number. Sorry.
To infinity and beyond.
Yeah, I know already, Buzz. There's no such thing as beyond infinity, Buzz. There's just infinity, but okay. Here's the definition of the exponential number. You're looking at what's called the limit here, ladies and gentlemen. They're saying what happens as x gets big forever there. It's getting bigger and bigger. That the value goes to this number, and this is the exponential number, ladies and gentlemen. As you guys can see, the pattern doesn't repeat. Its pattern, this decimal goes on forever. It's another example of an irrational number because it satisfies that definition. So the most popular irrational numbers, if you guys remember, these are some of the most popular irrationals. You have the square root of 2, pi, and e. These are the most popular irrational numbers that exist. And so you just learned a new one today, and this is a very, 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 very big deal because what happens now is we get to replace this whole thing with that number called E, ladies and gentlemen. And so the focus now, we have a very new formula. Okay? The new formula we have today here, if I get rid of all of this, this is called the continuous interest formula. Okay? This is the continuous interest formula. You have the number E, and the power now is RT here. And this is how things behave when things grow continuously. And this is now our continuous interest formula. And that's what would happen if you could get paid your interest continuously, not every day, not every hour, not every minute, not every second, but continuously. And so we can now answer that kind of question here. If we remember what we had, remember our interest rate here now was this. Remember, they started this whole process with this question here. So we want to know, what does our money become if we could get paid our interest compounded? Let's change this word here. Continuously. And that's the new formula that we use to answer a continuous interest situation. So again, the initial amount in this problem is $500. That doesn't change. That's right here. Start with your 500. The interest rate is 8%, like we were looking at. So that will be 0.08. The time, I don't remember what color we did for time, but our time was 35 years. Oh, I guess it was gold. So this is 35, ladies and gentlemen. So in your calculator, we're going to learn how to punch this in. Okay, here's the starting amount. Here's the seed that we had. Here is the interest, 8% as a decimal, and this is the time in years of 35. So this is the continuous interest formula. This is what we're going to punch in the TI now. We just have to get out the TI. But I wanted to show you guys where this number E comes from because it's an extremely important number to deal with. Okay, so ladies and gentlemen, here we go. We're going to go to the TI now, and the TI knows this number, by the way. If I put in, see this key down here? This is E. This is what we're looking for. Okay, that's the E. I'm going to put E to the first power here so you guys can see what E to the first power is. E to the first power, ladies and gentlemen, this is E to the accuracy that the calculator can give it. Okay, whatever number of decimals of accuracy, 1, 2, 3, 4, 5, 6, 7, 8, 9. Excel, 1, 2, 3, 4, 5, 6, 7, 8, 9 as well. It should be very similar. But ladies and gentlemen, we're going with this TI since we're going to enter it in the TI here. So we're going to start. We're going to put 500 now. And then put second E. Now I'm in the power position. The rate is 0.08 times that 35. 8% times 35. So this is what you end up getting, ladies and gentlemen. If you can actually get paid interest continuously, okay, not every minute, not every second, but continuously, you would get $8,222.32. Okay, you always approximate money to the nearest penny, because if you get a check, you want it to the nearest penny. So this is where we're at, ladies and gentlemen, to actually try to find what we get in a continuous situation. So you now have the continuous interest formula, and that's a big deal because there's some processes that do behave continuously. And this is one. So anyway, ladies and gentlemen, we're going to give you guys an example now. I'm going to have you guys try this. Let's take a look. I'm going to change this. $1,200 invested at 9.5%. Done for 40 years. Question 1. Two. Let's see. 1,000. 6.5%. 28 years. Okay. We're going to give you guys a few minutes to try this out on your own to get out your TI calculator. See what you get. Try this out. Let's see how this goes. All right, what kind of answers did you guys get? Remember, this portion you guys get to use your calculator. What kind of answers are you guys getting here? Okay, you're going to use the compound. You're going to use this formula here, the continuous interest formula. So A naught E to the RT. So I need to know what's the initial investment. $1,200. What's the annual interest rate? Well, that here is 9.5%. So that's going to be 0.095. So it's 0.095. The time here is in 40 years. This is T. So you punch in 1,200 E to the 0.95 times 40, ladies and gentlemen. This is what you enter. So remember these important values and where they belong. This goes here. So here we go. 1,200 times the second E, 0.095 times the 40-year investment. And ladies and gentlemen, your $1,200 grows to $53,641.42. That's what it grows to. And that's what we're looking at, ladies and gentlemen, how to use the compound interest formula. Okay, this is continuous growth. And this is a model that's used in a lot of different settings. Science settings, ladies and gentlemen. You know, it's used in these settings. So I want you guys to learn how this model works. Things that grow continuously. You know, a lot of things happen that way. Initial investment, $1,000. Annual interest, you have to know 6.5. That's the numerical representation, 0.65. Goes right here. And then the time in this case is 28 years. So you guys want to know this stuff. 28 years for time. So we get the amount being 1,000 E to the 0.065 times 28. So ladies and gentlemen, here you goes your 1,000. This is the interest rate, and this is the time, and this is the letter E, the number E, the exponential number. So let's get those values there. Let's see what this becomes. 1,000 times E raised to the 0.065 times 28 years. And ladies and gentlemen, $6,171.86. And this is what we get. Here it is. And that's the investment on $1,000 at 6.5 interest for 28 years becomes this $6,171. So ladies and gentlemen, you know, absorb this phenomena, because this phenomena is something that is used in different settings. And this is what you guys are here to learn. You know, we have the investment questions, and then I'll say, by the way, this is also used for population growth. You know, so if we look at question number 15 and 16, right? I'll look at 16 here. You know, money doesn't grow, but so does population. So we have something called population growth, ladies and gentlemen. And I'm going to put that down here. That P for population, if you have an initial population, a start population, they'll put e to the kt now. Now you might say, what about r? Well, it's the same thing. It's just when you change the setting, they'll use a different letter for that rate. So k represents, that same percent. It's the average growth rate. And that's going to be in the form of a percent. And of course, t still represents time. P naught is an initial population, starting population. And t is time in years. So I'll give you guys a few seconds to write this down. All right, let's try to use this, ladies and gentlemen. So if we go back and we look at the browser there, I want to ask you guys here. It says ELAC's population in 2000, right? In year 2000, what are they saying? The population consisted of 15,000 students. And then it says it has grown at an average rate of 4% per year. So that means K is 4%. And written as a decimal is 0.04. So here's the question for number 16. What is ELAC's population in 2015? So they want to know what's the population in year 2015. So let's go back. Year 2000, 15,000 students. Okay, so this is going to be what we start with. Okay, this is your P naught. And the average rate increase is 4%. That's how we write 4%. That's the K value. And then when they say year 2015, let me ask you guys here. What would the time value be going from 2000 to 2015? What would that be? Let's ask you guys here. See if you guys are awake. What's our time going from year 2000 to year 2015? What would T be? Right, you guys know? Thank you, Jose. T is 15. That means 15 years later. Thank you, Sarah. Good job. 15 years later. So when we use the same formula here, this is just like money. Population grows just like money's supposed to grow in a continuous sort of way. So you're going to replace this P naught. That's like your starting population, like your starting investment, 15,000 though. But the rate here is 0.04 and the time is 15. 15,000. 4%. There's your K. T is 15. So we're going to enter this in the calculator. We're going to put 15,000 e to the 0.04 times that 15. So we're going to put that in here, ladies and gentlemen. $15,000 times E 0.04 times, that was 15 years. So this is what will happen. Now, we're talking population. Now, let's use some common sense here, okay? You grow to the nearest whole number. You don't have decimal value. So this is going to be approximately to the nearest ones. Money's to the nearest hundreds because it's like a check. But for people, and that's not 1, this is going to be 2. So you're going to approximate to the nearest what's called ones position. And so, ladies and gentlemen, you're going to go from 15,000 students to 27,332 students with a 4% growth rate. And that's your growth rate at 4%. And that's how we go about a population growth kind of question. Anyway, I want you guys to know population just doesn't grow. Population can decay. And by decay, what we mean is it works backwards. Instead of growing, it could decay. But I want to kind of mention something like this. This is what the model for population growth, if you want to look at a model here. Okay, so I'm going to show you both population growth and population decay. Remember, E is approximately 2.718. So if you were to kind of graph this visually, to kind of visualize this growth here, you can start here. This is your time, and this is your P. So we start at time is 0, right? This is T is 0. T is going to be greater than or equal to 0, positive time. And remember this, that population grows exponentially because this is exponential growth. So what you're seeing here is a curve, and you say, where's the negative portion? We don't have negative time. We have positive time. So the kind of question that's modeled by this situation is that you'll say, start at 15,000 and through time, this could even be that 27,332, and this is my time at 15 years, because time could be in years. So your population is going to grow on forever at that rate, 4%. So you're going to get bigger, bigger, and bigger here. So I'll put this number 27,332. You can see it better. But that's the idea of the model of an exponential growth. So increase your time, the population gets bigger and bigger. Compare that to, you can have a population decline here. Also known as a decay. The only difference is that you're going to have a negative value for the rate. What they'll do is they'll write it down this way. They'll give you this negative sign here for population decay, and it goes in the other direction now. So generally speaking, as your picture looks, if I draw a general picture as opposed to a particular picture like the last example, you can have an initial population, P naught here. Time again is positive. It will now do the reverse. It'll decay forever. And that's your population decay. So it's kind of similar. You might say the time value is always greater than or equal to 0. They restrict the domain for time. But for decay, I want you to know they have a negative sign in this model. So we'll talk about that detail, but we'll look at an example. Like, for example, in the browser, number 18, they have a population decay, ladies and gentlemen. You go, why do I handle a population decay? Well, it's not just people that grow. Bacteria can grow and bacteria can decay. So in this situation, so you guys know, sometimes, like for Thanksgiving or any barbecue, I mean, the thing that I do is I get my food in the refrigerator as soon as possible, and then I freeze it as soon as possible. There's certain rules in the judge house regarding food storage, okay? You guys know you don't want to leave your food out at all if you can help it. Get it in the refrigerator as soon as you can, because bacteria grows exponentially. So I have some bacteria growth questions here too, like 17. Bacteria experiences, growth and decline. It can decline at a rate if you take bacteria antibiotics. But generally speaking, your food is gonna have an increase in bacteria. And so this is how you get sick. Does anybody know what's the general rule for your food? What's the general rule? What do you guys know about food and bacteria? How often, if you eat something and you get it in the refrigerator, how long do you keep it in the refrigerator? What's the general rule for you guys? What do you know? What's that limit? There's a limit. You can't just keep even food in the refrigerator forever. It'll go bad still because the bacteria grows. It may grow slower, but it still grows. Thank you, Sophia. Good job. You can hang at the judge house because, yes, 2 days is generally the limit, ladies and gentlemen. There's a 2-day limit. 2 days, I'll tell you. 2 days, and yes, that's a max. 2 days, yes, Ulysses, just 2 days. Outstanding. You guys know, because if you eat food longer than that, you might get a stomach ache, and something else might happen too that's not very pleasant. Okay, if you guys ever notice that, 2 days is the limit. Now, if you said, I want to keep my food longer than 2 days, because I had some Thanksgiving food I wanted to keep longer than 2 days, because I can't just eat Thanksgiving for, you know what I mean? I can't eat that stuff every day I can't eat the leftovers for 2 or 3 days. So what I did is I transferred the food to the freezer. Now you can leave it longer in the freezer. And yes, Sarah, you can hang at the judge home. You can freeze it. Yeah, and there's limits to freezing too, and generally it's like a couple of months, 2 or 3 months, I don't know. But there's limits for even freezing. So ladies and gentlemen, I just want to let you guys know this is all down our alley with this population growth and population decay, because remember, if your bacteria can grow just like people and money. But you might say, well, how do you make it decay? Well, if you get sick, they'll give you antibiotics and yogurt. They'll help a population decay or decline for bacteria in your stomach. So if you look at question number 18 here, this is a population decay question. This is kind of what I'm talking about. I want to decay that bacteria down to nothing because I have a stomach ache, so I'm taking antibiotics. This is how they work. So if we look at this situation, and they say in 18, bacteria experiences antibiotics, declines at a rate. So they have a decline rate. Notice that rate of decline in this question. That's 5% per hour. Okay? So this is K being 0.05 now. So already they gave us a decline rate. 5% per hour, that's pretty good. The bacteria will decline at that percentage, 0.05 every hour. That's great. But what they're saying is that's at noon when you apply your antibiotics. So evidently at noon, they had a particular starting of 8,000 bugs. That's a population. You start with 8,000. Okay. Noon, 8,000 pieces of bacteria. That's your P naught. And the rate is 5% decline per hour here. And then what do they say? How many pesky bugs will be present at midnight on the same day? So at noon to midnight now. Does anybody happen to know? That's 12 p.m., right? 12 p.m. and then at noon, noon is 12 p.m. Midnight is 12 a.m. What's your time value? What is T, ladies and gentlemen? If you go from 12 to 12, how many hours went by? Because I guess they're going to make us work for this. How many hours went by? Thank you. Thank you, Sarah. 12 hours went by. So in this example, our time is 12. And thank you, Jose. Thank you, 12 hours went by. Now, this is a decline situation here. So if this is a decline, what I want to remark here now is you're going to start with the 8,000 bugs population. 8,000. The rate is a decline. It declines at 5%. That's 0.05%. Thank you, Undead Horror. And thank you, Ulysses. Time is, in fact, 12. So this is 8,000 e to the minus 0.05 times that 12 now. Okay, because like before, T is 12. The rate, though, notice there's a negative value now in front of that value here. It's negative here. And the initial population is 8,000. So we can punch this in the TI in your calculator as well, and we can get these answers here. We're going to know you went from 8,000 bugs at noon. And we put 8,000. That's the start. Times that E. Now, negative sign is down here. Negative. Don't put subtraction. You'll get an error. 0.05 times the time value. And this is going to give us the new population 12 hours later. So, ladies and gentlemen, what you'll see is that there's 4,390 pesky bugs 12 hours later. And this is at midnight, ladies and gentlemen. Okay? So, this is how antibiotics work. You went from 8,000 to 4,390. So, if you had to model this, doctors look at this kind of stuff. They go, okay, 8,000 and the antibiotics, this is 12 hours later. Doctors look at these graphs. 4,390. That it's going to decline. And then you might want to say, what would it be a day later? If you're on antibiotics for a day. So I'm going to say, let's note. What if T is 24 hours? Right? How do you feel the very next day? So the very next day, if we change our time now, not to 12, let's see. What should that be a day later? Well, just change your time. The time was in hours. So the time is now 24 in this model. So if we said, okay, 8,000 times second E to the minus 0.05 times that 24 hours now, ladies and gentlemen, you end up with this time here being P being 2,400 to the nearest bacteria. That's 10. 2,410. So 24 hours later, there's 2,410 pieces of bacteria, little pesky bugs. And you guys, just to give you guys another note, how often, if you've ever been sick, how long do they want you to be on some of those antibiotics? You guys know? How often do they put you on antibiotics when you get sick? Remember what they give you? They tell you, like, does anybody know? You ever get an antibiotic? What about if it's 3 days? So what's my T for 3 days? Isn't that 24 times 3? Yeah, sir. We're going to try this out. We're going to do 3 days, and then we're going to do 7 days. Okay, so 3 days. Generally, they do like a 7-day. They might even do 10 days. So this is 24 hours times 7. You say, well, what's the bacteria going to be after 10 days, right? This is why they make you take that bacteria. I'm telling you, you guys, you're learning something here. Okay, and I'm going to share with you guys, if you said, well, what is 24 times 3? Right, is 72 hours. 24 times 7 is 168 hours. 24 times 10 is 240 hours, ladies and gentlemen. So let's try to see what our bacteria becomes with these particular time values. So if I go to the TI, 8,000 times E, negative 0.05. Now this is the 3-day. That's 72 hours here. This is the 3-day, ladies and gentlemen. I'm doing that 3-day. And then we'll do the 7 days and the 10 days. And so what you get here is, ladies and gentlemen, after 3 days, the population is going to be 219. And you should be feeling after 3 days very good, a lot better than you did with the 8,000. Okay, so you should be feeling very, very good after 3 days here. So in honor of Thanksgiving, let's see, how do we feel after 7 days? What would 7 days look like? Well, you started 8,000, got you so sick, negative 0.05 times 7 days was 168 hours here. So you're now, after a week, this is why they tell you, hey, take this stuff for a week. Don't get off of the bacteria. If you go to the nearest whole bacteria, that's 2. 1.7 is about 2. So there's only 2 pieces of bacteria after 7 days. This is why they say take it for 7 days straight and don't ever stop taking your bacteria or your antibiotics, because you want to have that population decline. All right, ladies and gentlemen, this is real. This is the real deal. And then you say, well, okay, why did they tell me take it for 10 days straight? Well, I don't know. Maybe they say 10 days. I always remember 7. 10 days. Oh, we'll see. After 10 days, that's 240 hours. Let's see what the TI says. 8,000 times second E, negative 0.05 times 240. And ladies and gentlemen, your population is approximately 0. So that means the population is approximately gone after 10 days of antibiotics here. So maybe they do want to say, hey, go all the way to the 10 days and don't stop. But this is what doctors look at, ladies and gentlemen. They look at these graphs and they have to understand about exponential decay like they have to understand about exponential growth. And when you have decay, the rate here is negative. They always say, they're going to give you language like K is positive, but opposite that, this minus K will be negative. Okay, so they're going to give you the language being positive, that rate, and that's, you have to understand the model, meaning is it a decay situation or is it a growth situation? Because for graphs, if you guys recall, and give you a definition, we do have something called the exponential function. The exponential function, ladies and gentlemen, where f of x is e to the x. That's the one and only exponential function. Remember, e is approximately 2.718. So that means this is a growth function here, just for e. You might say, but then how come, if they give you a function that looks like this, they say, what is e to the minus x? This is not growth. This is e to the negative 1 times x, e to the negative 1 raised to the x power, and this is by properties of exponents, 1 over e to the x. So this is a decay function when you have that negative sign there. So that's why this one's decay. And so even if you said, hey, Desmos, do you know about these functions? Do you know about e to the x? Desmos will say, I sure do. Y equals e raised to the x. There's your e to the x function. That's exponential growth, ladies and gentlemen. Y equals the negative e raised to the x power here. Oops, that shouldn't be, that should be negative up here. Negative e to the x in red, this is your exponential decay curve, ladies and gentlemen. So I have exponential growth, exponential decay, and that's because of the value of e. You got e is approximately 3, but 1 over e is approximately 1/3. So, this is why you see what you see in the graphs here, exponential growth and exponential decay here. So that negative power is a factor. And so, ladies and gentlemen, take a look. These are the things that were on that worksheet here. If I go to the browser,